but the standard deviation is high. In some cases, well, the average storm flow runoff is about 7% of total annual flow, but there's variability in all cases. And the watersheds themselves have different characteristics. So this is turning out to be a really nice place to work because in a small area that is relatively close to the university, we can have long-term instrumentation and investment in field observations so we can get there and do work, but it's not just that it's convenient. It happens to be very interesting hydrologically and lets us ask interesting questions about what's going on in the subsurface, the surface, and vegetation characteristics that are driving all of these different changes. And I'll sort of lead through some of the discussion on what we think is going on. So we're going to talk a little bit about how we're using field experiments at a rate of scale to understand processes now. So this is the schematic of the heavily instrumented small watershed that operates differently in terms of annual hydrologic response than the rest of our watersheds. And we have a couple of very intensive measurement points. So in this particular case, we have a full meteorological tower, we have sub-canopy flux being measured, we have a couple of other rain gauges, we have soil moisture sites, we have a bunch of snow monitoring stations, and then we have a very heavily instrumented hill slope area that we do continuous monitoring of electrical resistivity in the subsurface that allows us to look at changes in moisture status, along with soil moisture probes to validate some of that work. We also have a hill slope trench that is cut into the side of the hill, and that is leading to some fairly interesting outcomes already. I want to tell you about a couple. And one of them is that if you look at the way in which evaporation comes off of that hill slope, it is relatively interesting to see that, and what this graph is showing you is that these two lower lines here are the upper trees in the upper part of the hill slope and trees at the lower part of the hill slope. So sort of near the ridge and then down near the valley bottom are not contributing an enormous amount to the total annual budget of evaporation off that hill slope. Where most of the evaporation is coming out as a function, or transpiration out of trees, is off the mid-slope, which I guess to me ran a little bit counter. I was expecting when somebody shows me a graph like that, I'm going to think that these are the trees down in the lower part of the watershed near the toe of the hill, but it's not true. The other part of this that was published a while ago, and I'm sure I don't have a graphic of it, was some work that came out of Brent's lab looking at how much moisture is lost through sublimation annually, and this is becoming a pretty interesting topic nationally and internationally, and it was like 30%, is that the right number? Around 30% of the annual moisture is sublimated, which is not, that's a big number if you're not thinking about the way in which moisture is lost to the atmosphere. The hill slope trench study is something I just want to bring up because it allows us to look into how water moves through the subsurface and out. And what is going on here is there is a trench dug into the hill slope, and then water that moves out of the soil is then captured and routed and measured, and then water that comes over the surface is captured and routed and measured. So we can look at flow across the surface and also flow coming out of the soil. And this graphic right here, what we're seeing is water in the surface. It's this blue, so this is March through June, and so early in the snowmelt season, you see little pulses coming off the surface. That might be moisture just melting right into the surface trench out of snow, or surface runoff running down into the trench from underneath the snow and then being routed out. Can't be sure entirely what's going on in the surface trench because it's covered in snow at that time of year. I want to draw your attention to this part though. These red bars here are the total amount of water that's coming out of the soil. And so what's happening in this particular case is that moisture is going from the snowmelt into the soil, but it is not migrating out into the trench during the snowmelt, early part of the snowmelt season. So melt is occurring throughout, but then only when you get to sometime in the middle of May do you see water actually migrating out of the trench, moving out of the soil profile, and then coming down. So that links to these points, or these lines down here. These are soil moisture profiles, and what you see here, this is 90 centimeters near the trench itself, and it's bopping along here at about 22% volumetric water, and then you see it get pretty wet, and then water starts coming out. Every time it spikes high moisture content, you see water being shed out of the subsurface. So this is a way that it's going to allow us to understand how moisture is moving down to the subsurface. So to better quantify the characteristics of soil and subsurface movement, we have an experiment going on where we take hill slope plots. In this case, these are over on the Laramie Range, and you can monitor flow across these plots for natural events, but we can also rain on them using a simulator and then look at what's happening under a controlled experiment. And so I'll walk you through outcomes of a couple of controlled experiments that are pretty interesting because they shed light into surface runoff and near surface processes. So in this case, what this experimental design does is it rains at known or governable intensities, and basically you saturate the surface with a lot of rain and then you crank up the intensity, and you can look at saturated hydraulic conductivity, the total response of runoff to rainfall events, and so on. And then in this particular apparatus, the innovative piece that we're doing here at Wyoming, not to say rainfall simulation is not innovative, but it's been done for several decades. We have added resistivity here. This is Austin Carey. He is a master's student working on this particular project. And you can look at how the resistance in the subsurface changes as you wet it up. And so this is a time-lapse image of the change in soil moisture status below the simulator. And in this case, this is a coarse upland ecological site, and the simulator sits on top, and you can see it migrating down into the subsurface and also a little bit laterally. And I'm going to compare this to the next site, which is a different ecological site. This is a shallow upland. In this case, the simulator sits over here, and you can see it not penetrating to as deep an area or deep a depth as the coarse upland, and it moves laterally. So you have a different hydrologic response, even in this shallow subsurface, to these different events, which gives us insight into how we might expect them to respond to rainfall runoff or snowmelt in the future. I'm going to touch on this a little bit. Andy, I think, is going to talk about it a little bit more. I'm looking at him to see if he's going to nod. Yes. Okay, just making sure. This is a partnership project with the Game and Fish, where we're up in northwestern Wyoming looking at how return flows that are applied from an agricultural field make it back down into the river. And I'm just going to give you a quick highlight here, which shows that if you put, again, we're looking at resistivity in the subsurface. If you apply water onto it, our little video is not working. Oh yeah, I don't have the mouse. That's okay. I'll let Andy hit it as a better highlight. So in this particular case, we can look at how water applied onto the surface moves into the subsurface and then measure how it's making its way down into the stream. Those of you who are interested in Wyoming water know that aerial or subaerial irrigation of meadows and how much water makes it down into the stream is a very interesting topic for a variety of reasons, one of which is very hydrologically interesting. It's a great controlled experiment beyond the other aspects of water allocations. Last piece I'm going to touch on is how we try to tie a lot of this work together in terms of observations to interpretation and modeling. So we have some very talented people in the modeling crew that are trying to figure out how to take some of these field observations and then put them into a coupled surface and subsurface model. This is a very active topic in hydrology, and it's only recently becoming really impactful in the sense that we have computing resources that we can really take advantage of. So we have some people on the project that are very good at working with high-performance computing and taking large-scale data and moving it into an operational setting. And I'm looking at people like WyCEHG and Po Chen and Thijs Kelder's and their students who do this kind of work really well. So in our case, what we've got are some projects that are working on taking field observation data and running them with sophisticated models to interpret hydrologic outcomes. One of the models we use is called ParFlow, and this is a representation of how we model the no-name watershed And what we are trying to figure out how to do is take the geophysical data that we use from seismics and resistivity and NMR and all these other terrific instruments that Steve outlined, and put those data into a model to represent the subsurface. It's kind of a boring schematic, but it shows you that we are that we can conceptually break the landscape into little cubes, both vertically and horizontally, and assign each of those a parameter that we're going to pull out of the geophysical data. So this is a way that we're trying to advance our understanding of hydrology. This is relatively new work that I'm going to present, but I think it's very cool because it shows the path forward for how we can link our hydrological observations with our geophysical observations and our modeling to try to tell a story of how water is functioning. So this is the No-Name watershed. I'm going to show you some work that was done by the geophysics field team. Brady Flincham is a PhD student, did some of the interpretation here. And we did some intensive geophysical field observations on this part of the watershed and on this part of the watershed. Water drains in this direction, comes out here and out. Now remember, this is the No-Name watershed where we said that there is relatively little runoff as predicted based on all the other observations that we have in the region. So this is a system that you might classify as leaky, or that loses a lot of water to groundwater systems. So let's kind of try to walk through how this might be interpreted. If we look at the upper boundary of the watershed, these are geophysical imagery. This is seismic velocity, and remember what Steve said is, as you look into the subsurface of seismic, you can try to interpret the areas that are intact bedrock, fractured bedrock, saprolite. Can't really see the soil with this, but we know that the soils up there are relatively thin, less than a couple of meters, generally speaking, often much less than that up on the hill slopes. And what we can do is look at the depth to bedrock and the depth through the weathering zone up on this part of the watershed, and compare it with the southern part of the watershed. And what we see is as you move down the watershed, it becomes much deeper and much more fractured is our interpretation. And so the interesting part about this is that we see as you move down to the outlet of the watershed, these are sort of abstract representations. You'll have to take my word for it. This is getting close to the outlet because we don't have a watershed boundary on it. But if we go back and forth, you can see near the upper part of the watershed, we have a relatively thin area. Down to the lower part of the watershed, we have a relatively thick weathering ride and some what we might interpret as fractured bedrock. Here's the interesting hydrological story. If you go right outside of the watershed boundary, you walk into a very small hill slope contributing area, but there is a very active stream that pokes out, and it's a very identifiable spring. We put that here as this star. So if we put ourselves in context from a map view, there's a spring that pops out just outside the watershed boundary and contributes runoff outside the watershed. Thanks to the LiDAR data, we have a pretty good representation of terrain. But even when you're out there, it's pretty obvious that you are outside of the watershed. This is a small contributing area to this spring, and so it begs the question of how do you have a pretty active spring in a large river, or not river, large stream, when you have such a small watershed? Well, one of the things that you can pull out of the geophysics data is that we have a potential route in the subsurface that would send water from this upper part of the watershed down through what might be perceived as a leaky underground aquifer. So in this case, we would not match our ground watershed with our surface watershed, because the ground watershed might be running water out through the subsurface rather than routing it out through our watershed outlet. So to kind of wrap this up, this might be a way that we know that this watershed does not produce a lot of runoff, so we might classify it as leaky, but right outside the watershed, we have indications that there's a pretty large spring that might be the source of our water that would otherwise be coming out of our watershed, and then we use our geophysics data to try to interpret that connectivity. Now the task that's ahead of the hydrologic modeling group is to take those seismic and resistivity data that I didn't show you and infuse those into a model to see if we can represent these or turn these observations into a modeling construct. It's very interesting in terms of how this path shows hydrology, geophysics, modeling outcome, and our understanding of what's going on in the landscape. Okay, to wrap up, Steve walked you through some of the high-impact work related to the critical zone and the work on soil water equivalents, and then I sort of gave you several highlights of some of the areas of research that we think might tie into the people in the room's interests. Don't forget that there are other talks today, and then later today there will be some posters that will go into greater depth, and you can have a chance to interact directly with some of the research scientists that are working on the project. And with that, thank you very much for your attention, and if you have questions, I think we're coming up pretty quickly on the break, but we might have time for a couple now, but I know Steve and I would be very happy to chat or point you in the direction of the other really talented people who did all of the real work that we're sort of standing in front of.
Yes, so there's a couple of questions for Scott and Steve. We have a couple of minutes if you want to ask questions about this presentation.
I'd just like you to go into a little bit more the difference between groundwater watersheds and surface water watersheds and what some of these tools can tell us about that.
Sure. So the question was just to talk, or asked to talk a little bit more about differences between surface watersheds and groundwater sheds. And in a case like this, I guess in a normal watershed and groundwater interpretation, we might expect that the groundwater orientation, the directional flow of groundwater in a system would be essentially the same as the topography. So barring any other knowledge, where you don't have groundwater wells and you can't infer subsurface direction because of pressure head, we don't have any pressure head information or anything like that. At a first order approximation, we would assume that the groundwater directional flow would map with the topography. And so then what you would end up with is the groundwater pressure being expressed within the channel that is inside the watershed as water is contributing through the groundwater and coming near the surface and coming out. In this case, we don't see that. And so what we might see, or what we expect to see in cases like this, is that the groundwater is moving in a direction that is not the same as the topography. There are a couple of pretty clear cases like this around the world. It's not novel in the sense that people know about groundwater, surface water, non-directionality. But in this case, I think we've zeroed in on how we might interpret it without going in and digging a bunch of holes and looking at pressure